In this video, I will show you how to use the first derivative to determine the intervals where a function is increasing or decreasing. So when we're talking about increasing and decreasing intervals, graphically you should be looking at the function from left to right. And we know that any interval where the function is falling, that's going to be a decreasing interval. And where the function is rising from left to right, we're talking about an increasing interval. So where are the increasing intervals on this particular graph? We see that the function is rising from A to B. So we have an increasing interval, the open interval AB. We use an open interval and exclude A and B. We write parentheses, not the square bracket, because right at A, the function is neither increasing nor decreasing. There's a slope of 0 right there. So we have to leave out the endpoints here. Are there any other places where the function is increasing? No, I don't see any. So how about decreasing? So the function is falling from here to here, starting at negative infinity. Now, I purposefully drew a graph that starts off up in the sky to make it clear to you that when we say negative infinity to A, we are talking about x values. We're looking at the x-axis. So when I said from A to B, notice that these are x values. It has nothing to do with the y values. So when I say from negative infinity to A, I mean because this graph is coming in from the left. Negative infinity is over here on the left, so that's why it's negative infinity. It's a common mistake for students to say positive infinity because it's pointing up in the sky. No, that's a y value thing. X value wise, this is negative infinity to A. Are there any other decreasing intervals? Well, we see that the function is also falling from here to here. Now, looking at the x-axis, that is between B and C. So there's another decreasing interval, the open interval from B to C. And we use a little union symbol to connect them when there's more than one. There's also an interval where the function is constant. You see that the function is flat right here, and that is from C to positive infinity. Okay, now, what about derivatives though? Remember that the derivative represents the rate of change, the slope of the function. So look at the increasing interval from A to B. What do you think about the slope of at any point in this interval? Well, so for example, right here, all right, the slope of the tangent is about like that. Notice that is positive. If you pick a different point, okay, for example, right here, again, that is a positive slope. I'm going to pick one more point closer to the end point here, and that slope might be about like this. So I'm getting different slopes in here, but notice that they are all positive slopes. So that means that along this entire increasing interval, the slope is always positive. In other words, the derivative is always greater than 0. Similarly, if you look at a decreasing interval, like from negative infinity to A, you can very quickly see that we're looking at negative slopes in that interval. So the derivative in a decreasing interval will always be less than 0. And of course, for a constant interval, it's horizontal. So the slope is 0. So therefore, the derivative will equal 0 on a constant interval. A, B, and C are called critical numbers. Critical numbers are values where the derivative is either equal to 0 or undefined. So, for example, the derivative at A is equal to 0. Notice that the slope of the tangent line is 0. That's why a is a critical value. Similarly, the derivative of f at b is also equal to 0. Slope of the tangent line equals 0 there. C is a critical value because the derivative is undefined. All right, f prime at C is undefined. When you have a sharp turn like this, boom, boom, the derivative is undefined because the slope, the limit from the left and the limit from the right are two different numbers. So that makes the derivative undefined. So just keep that in mind. So notice critical numbers are the only places where a graph can go from decreasing to increasing or from increasing to decreasing. All right, we're going to use that fact to determine increasing and decreasing intervals. Example 1, find the open intervals on which f of x equals x to the third power minus 3 over 2x squared is increasing or decreasing. So step 1. Step 1 will be to find the critical numbers. Remember that the critical numbers are the numbers where the derivative is either equal to 0 or undefined. So, of course, that means we have to find the derivative. So we will do f prime of x equals, we're doing the power rule, so the 3 goes in the front, and we decrease by 1, we have 3x squared. Here we will multiply 3 over 2 by 2. The 2's will cancel out, and we'll have minus 3x. You decrease this by 1, and it's just x. And that's it. This is the derivative. So all we have to do to find the critical numbers is set this equal to 0. And that way we'll find the values where the derivative is equal to 0. Notice there are no denominators or anything like that, so there's nothing to cause the derivative to be undefined. So setting this equal to 0 and solving will give us all of the critical numbers. So we will set 3x squared minus 3x equal to 0. Both of these are divisible by 3, so might as well do that. Divide both sides of the equation by 3. That's going to give you x squared minus x is equal to 0. Pull out a common factor of x. So you're going to have x times x minus 1 is equal to 0. Using the zero product property, we can set x equal to 0, and we just have x equals 0. And if we set x minus 1 equal to 0, that's going to give us x equals 1. So these are the critical numbers. Step 2, use the critical numbers to separate the number line into intervals. So our critical numbers were 0 and 1. So I've separated the number line into 3 intervals from negative infinity to 0, 0 to 1, and 1 to infinity. Step 3 is to pick a test value in each interval to evaluate the derivative. So in the first interval, I'm going to pick negative 1. You can pick any number you want as long as it's in the interval. In the second interval, I'm going to choose 1/2 or 0.5. And in the last interval, I'm going to pick the number 2. So we need to evaluate the derivative at negative 1, and we'll evaluate the derivative at 1/2 and the derivative at 2. And all we really care about is whether or not the derivative is positive or negative. Okay, the actual value is not important right now. So remember, we have an expression for the derivative, 3x squared minus 3x. So that's going to be 3 times negative, 3 times negative 1 squared minus 3 times negative 1. Okay, and so will this be positive or negative? Well, when you square the negative 1, that's going to be a positive 1. And positive 1 times 3 is just 3. And here I've got negative 3 times negative 1, so that's going to be a positive 3. So this is definitely going to give us a positive value. All right, so that tells us actually that in this interval, the function must be increasing. Okay, we must have an increasing slope. So what about 1/2? So if we do the derivative at 1/2, that's going to look like this. So this is going to be 3 times 1/4 once you square that. And so I've got minus 3 times 1/2. So I've got 3/4 minus 3/2. All right, 3/4 is smaller than 3/2, right? 3/4 is 0.75. 3/2 is 1.5. So we're subtracting a bigger number from a smaller number. This will definitely give us a negative number. That means the slope in this interval must always be negative, which tells us that this is an interval of decreasing. All right, and for the final interval, okay, at 2, f prime of 2, so I've got 3 times 2 squared minus 3 times 2. So that's going to be 3 times 4 minus 3 times 2. So that's going to be 12 minus 6. That is going to give us a positive number, which means that we're finishing up again with an increasing interval. So what are the increasing and decreasing intervals? Well, we have our first increasing interval from negative infinity to 0. And we have another increasing interval from 1 to positive infinity. And then we have our only decreasing interval from 0 to 1. So I want you to notice how this gives us a rough idea of what the actual graph must look like. When we look at the actual graph, we should expect to see something like this. We know that the graph is going to be increasing and then decreasing and then increasing again. So we know the graph is going to be doing something like this: increasing and then decreasing and then increasing again. And we also know the x values where the changes happen, okay, because of the critical numbers. So at 0, okay, so this is going to be at, 0 comma something is where it's going to change from increasing to decreasing. And then we have a critical value here at 1. So we know right here at 1 comma something, this is where the graph changes. So let's go ahead and take a look at the actual graph of the function and see how we did. Actually, before we do that, let me not leave these y values as a mystery. We can easily find out what the y values are. We can't use the derivative because that just tells us the slope, and we already know that the slope is 0. We need to look at the original function and find out what happens if we plug in 0 or 1. So looking back at the original function, if I put in 0 here and here, that's going to give us 0. All right, so we can see that f at 0 is equal to 0. What about 1? If I do f at 1, that would be 1 to the third power minus 3 over 2 times 1 squared. That's going to give us 1 minus 3 over 2, right? Because 1 squared is just 1, so that just leaves us with 3 over 2. 1 cubed is 1, so we have this. But this is the same thing as 2 over 2 minus 3 over 2, so that's going to be negative 1/2. So these are the y values, 0 and negative 1/2. So we have 0, 0, and 1, negative 1/2. Okay, so that really kind of lets us know a lot about what this graph should look like. So this is 0, 0, so this should be right at the origin. Okay, and this is this looks deeper than it really is because it should be at negative 1/2. Now let's look at the real graph and see how we did. So here's a glance at the actual graph right off of Desmos. And as you compare that to our rough sketch that we did, we nailed it. So you can see how useful the first derivative test is going to be in helping us predict what the graph of a function will look like. Let's talk about relative extrema. If there is any interval on which f at c is a maximum, then f at c is a relative maximum. If there's any interval on which f at c is a minimum, f at c is a relative minimum. Okay, consider the closed interval from -2 to +2, which includes everything you see here. Look at this point right here, 0, 0. Would that be a maximum? No, because there are higher points over here. So this is not a maximum on the interval -2 to +2. However, this is a relative maximum because there is an interval on which this would be the maximum. For example, let's say if I said, well, let's just look at the interval from -1/2 to, is that -1/2? No, I guess I didn't quite go far enough. If I said, look at the interval from negative to 1/2 to +1/2, this is the maximum on that interval. So if there's any interval where this is the maximum, then this is a relative maximum. Similarly, this point right here is not a minimum on the interval from -2 to +2, right? If you look at everything you see here, this is not a minimum. You could pick any of these points over here. They are lower than this. However, this is a relative minimum because if you pick an interval from, say, here to here, whatever that is, this would be the minimum on that particular interval. So because there exists some interval where this point is the minimum, that makes it a relative minimum. Let's squeeze in one more example. Example 2, find the relative extrema of f of x equals 1/2 x minus sine x in the interval from 0 to 2 pi. So the first step is to find the critical numbers. And remember, the critical numbers are where the derivative equals 0 or if it's undefined. So that means we're going to need the derivative. The derivative of 1/2 x is just 1/2. The derivative of sine is cosine. Memorize that. So here is the derivative. So if we set this equal to 0, and solve, that will give us the critical numbers. Notice there are no values that will cause this to be undefined. So by finding the values where the derivative equals 0, that will give us all of the critical numbers. So let's add cosine x to both sides, and that'll give us cosine x is equal to 1/2. All right, so to solve this, let's use our imaginations. Okay, here's a quick sketch of the unit circle. Where is cosine equal to 1/2? We know that the cosine of pi over 3 is equal to 1/2. That's one of those values that we memorized, right? Cosine of pi over 3 is 1/2. Make sure you have this whole thing memorized. So that tells us that pi over 3 is the reference angle. All right, RA. Pi over 3 is the reference angle. There are 4 angles that have a reference angle of pi over 3. There's pi over 3 itself in the first quadrant. Okay, in the second quadrant, the angle that has a reference angle of pi over 3 would be 2 pi over 3. The angle that has a reference angle of pi over 3 in the third quadrant is 4 pi over 3. And in the fourth quadrant, it is 5 pi over 3. Okay, the cosine of any of these is going to give us some kind of 1/2. It's just that 2 of them will be positive 1/2 and 2 of them will be negative. Cosine is an x value. X values are positive to the right. All right, so x values are positive in the first and fourth quadrant. X values are negative in the second and third quadrants. Since we have a positive 1/2, these solutions are going to be x equals pi over 3 and 5 pi over 3, the two positive ones. So these are the critical numbers. Next, we take those critical numbers and we do the number line. So it's time for the number line. Okay, so here comes my number line. And I'm using my critical number, so I will put pi over 3 right here, and I'll put 5 pi over 3 over here. They gave us an interval from 0 to 2 pi, so we might as well put that on the graph. We have to stick to this, 0 to 2 pi. Okay, test values. Let's pick some test values to use. Between 0 and pi over 3 would be pi over 6, so that'll be a good value to use. I'm making sure to pick these values, or these, at least I'm using these as reference angles. Okay, so pi over 6 would be in there. Okay, what about between pi over 3 and 5 pi over 3? Let's look at our unit circle. So here's pi over 3, and if I go all the way around and back, then I'm getting to 5 pi over 3. I can pick anything between here and here, anything at all. So why not pick pi? That's nice and simple. Pi is between pi over 3 and 5 pi over 3. So I'm going to use pi as a test value. You don't have to use pi. You could pick other stuff. You could do 2 pi over 3 or 4 pi over 3 or other choices, pi over 2 or 3 pi over 2. Anyway, I'm talking too much. Now, between 5 pi over 3 and 2 pi, so that would just be in this little area right here. So I'm going to go with 11 pi over 6. So a moment ago, I just picked pi over 6, which is like right here. So I'm just picking the other angle that has a reference angle of pi over 6. And in my mind, I always say to myself, 2 pi is the same thing as 12 pi over 6. So if I go back 1, that's going to be 11 pi over 6. All right, that helps me remember that this is 11 pi over 6. So anyway, 11 pi over 6 would be between 5 pi over 3 and 2 pi. So I'm going to pick that. Okay, 11 pi over 6. So let's check the first derivative. So we have that nice expression. Remember, 1/2 minus cosine x, that is the first derivative. So that means we have to do 1/2 minus cosine of pi over 6. And remember, all we care about is it positive or negative? Cosine of pi over 6 is radical 3 over 2. So this would be 1/2 minus radical 3 over 2. Radical 3 is bigger than 1. So when I do 1 minus radical 3, I'm going to get a negative number, which tells me that we are decreasing in this interval. Okay, now let's evaluate the first derivative at pi. So that's going to be 1/2 minus the cosine of pi. All right, of course, cosine is the x value on the unit circle, and here at pi, that would be negative 1. So this is going to be 1/2 minus negative 1. Minus and negative is really addition, so this is going to definitely give us a positive value, which means that the function is increasing on this interval. All right, and the last section, evaluating at 11 pi over 6. So I'm doing 1/2 minus the cosine of 11 pi over 6. Remember, what matters is the reference angle, okay? And the reference angle is pi over 6. And I know that the cosine of pi over 6 is radical 3 over 2. So this is either going to be radical 3 over 2 or negative radical 3 over 2. Those are the only options. But remember the quadrants, 11 pi over 6. Cosine is positive in the fourth quadrant. All right, we knew that right away. So it's just going to be this again, the same exact thing we had in the first interval. So this is going to be negative again. All right, so that means another decreasing interval. And that is enough to tell us that we have a relative minimum at pi over 3, and we have a relative maximum at 5 pi over 3. Okay, so let's just write that down. All right, so we have a relative min at pi over 3, and we have a relative max at 5 pi over 3.